Good afternoon, folks. Thank you for joining us. I can't believe we are at 128. Seems like we were at 1 like yesterday, right, Grish? So we're going to talk about Fibre Channel and the roadmap and how we are getting to 128 and all the challenges. As you can imagine, the speeds, it gets, really, really difficult for us to keep on doubling the speed every 4 or 5 years. So Craig is going to really go into the details. So if you're a hardware designer, you're going to enjoy that part of the session. So again, Craig Carlson, long-time Marvell. I think he recently got a new job at AMD. I think AMD is really lucky to have you, Craig.
Thank you.
My name is Rupin Mohan. I work for Hewlett-Packard Enterprise. I've been with the company for, believe it or not, more than 26 years. So I know it's hard to believe. Fibre Channel Industry Association is it's a kind of a non-profit, and we really are in there, and to all of us, like 6 or 7 companies now. We meet quite regularly every 2 months to develop the standard, but also to do a lot of other things like interop testing and plug fests, etc. Because Fibre Channel, as you can imagine, it's really started the whole concept of shared storage. Before Fibre Channel, it was all direct connect, server attached storage. So this is a non-profit association. I highly recommend, if you're not part of FCI or you're not following FCI, you should. Recently, we started doing these educational broadcasts, webcasts, and those have become really, really popular. We have about 5,000 people who regularly view our webcasts, and the number is growing every month. And I think now we have more than 24 recorded sessions on Bright Talk. So if you want to just search for FCI Bright Talk, you can go and watch these presentations. And most people who watch these presentations are engineers, and our average rating out of 5 is 4.5 and above. So most people who look at our educational sessions, they highly rate it because they find the value in it. We've been doing Fibre Channel for 25 years. So like I said, I've been with HPE 26 years. I've been working on Fibre Channel since the day I joined the company, so it's kind of strange. I've been working with Fibre Channel since Gen 1. And we have a huge install base. Currently we have, I think, almost like $40–50 million 40–50 million Fibre Channel ports in production right now. And so it's really very popular in the enterprise. Anytime you find, anybody's talking about enterprise storage, it's running on Fibre Channel. And many protocols have come, try to displace Fibre Channel, whether it's FCOE, iSCSI, and now, NVMe. But, it's really been difficult to displace Fibre Channel. And with FCNVMe, you will see that our performance numbers are even better than the rest of the technologies. So the agenda for today, we'll talk about the milestones, talk about the nomenclature, terminology, and then we'll jump into the standard 128, and Craig is going to go deep into the signaling, framing, and the physical layer, which you will really enjoy, including the protocol changes that we're going to be doing and the roadmap. So, like I said, the Fibre Channel, we've been doing this work since a long time. Started with 1 gig, went to 2, 4, 8, doubling to 16, 32, 64, which is Gen 7, which is shipping right now. And then we're working right now on 128, which we will talk about today in today's presentation. And you will see that, Fibre Channel is really responsible for a lot of cool technologies over the years. Whether it's fabric services, name servers, discovering the whole fabric, discovering all the storage arrays, initiators, and really, connecting all the, shared storage to the servers, FCOE, converged networks over the years, NPIV, and now, most recently, NVMe running over Fibre Channel, which has been really cool. When I started working on Fibre Channel, we were working, and I was working on a TCP/IP driver running on Fibre Channel. So we were doing connecting Ethernet networks over Fibre Channel. So the protocol is really has survived over the years, and it's pretty robust. It was designed from scratch. We say that all the time. Fibre Channel was designed from the start for storage traffic. So it's really, you know, very reliable and deterministic protocol. If you look at the acronym soup, right, I think this is something that acronym soup, something what Craig calls all the time. FCPI is called Fibre Channel Physical Interface. Really, when we start a new generation, that's when we start. We start from the bottoms up because that's where the complexity lies in the bottom on the physical layer, in the hardware, and how to drive that, you know, really, on a single lane, that 128, gig, speed. And then from the physical layer, you go into the framing, the signaling, and then the protocol. So, as you can see, now we're 128, we're talking about PI8, which is what the team is working on. Another, some of the marketing sort of PRD requirements for any product, any standard, any bump in the standard we do is about, backwards compatibility for 2 generations. This is very unique with Fibre Channel. We've kept this as a sort of a religious, requirement that when we develop any new speed, we make sure that it's backwards compatible to 2 generations, and it's plug and play. Really, there's no manual configuration required either on the switch or the initiators or the storage arrays. Really, you just plug it, and automatically the protocol, comes and negotiates the right speed for that, interconnect. And then the other thing is, we always look at the cabling infrastructure for our customers who have deployed Fibre Channel. The cabling infrastructure is very sacred. It takes a lot of money, a lot of capital investment to put the cabling infrastructure in place. So asking any of our customers to, hey, you know what, we're bumping up the speed, now you've got to rip and replace cables, it's not something that flies very well. Personally, I have moved labs, within my own organization, and from one location to another location, and it's, at the end of the day, what we end up doing is basically cutting all the cables. That's the only way to get through this maze because it's so complex. There's no way you can pick one cable out of a maze and then replace it with a new cable. That's just impossible to do. So maintaining and supporting existing cables is a very important P0 requirement. The third important goal is the reach goal, which is 100 meters for us. Again, this is very religious for us. Most of Fibre Channel deployments are disaster, replication, synchronous, asynchronous, especially synchronous replication, especially in Europe. We see a lot of companies doing synchronous replication over dark fiber, and 100 meters is something that is a very important reach goal for us because, with the 100 meters, you don't need to put any expensive optical infrastructure to get to your other site. So, even things like, the Las Vegas Strip, you have all the casinos running Fibre Channel, pretty much all slot machines run Fibre Channel in the edge. And, you find, most casinos have DR sites across the Strip. So there's, the primary storage array is on one side of the Strip, secondary storage array is on the other side of the Strip, and they have dark fiber underneath the Las Vegas Boulevard, right? Just as an example. And then we'll talk about, all the bit rate targets we have. I mean, Fibre Channel does a fantastic job of error recovery, and it has the lowest bit rate, when it comes to any type of storage interconnect. And that's why, is part of the reason why recovery mechanisms are very, very robust. Most of the work is done on the ASIC level in Fibre Channel. We do most exception handling in the driver firmware levels, but most of the protocol runs on the ASIC level. And that's why, this protocol is really very hard to displace for storage interconnects.
For that bit error rate, how many errors is that in a minute?
Right.
I'll go into that.
Okay.
Yeah. Okay. Just as a milestone, we have just completed our PI8 single lane spec, and also in terms of FS6, framing and signaling spec, we just finished that, and then we have approved the PI9 project, which is the next generation project, right, 256. One more topic I want to discuss is we've done a very interesting educational seminar on machine learning and how Fibre Channel is well suited for these types of workloads. For machine learning, AI, machine learning, AI, ML workloads, Fibre Channel is a very interesting solution for shared storage infrastructure implementations. Of course, you can use all types of, infrastructure and architectures for, AI, ML. But we believe shared storage is the best way to run an AI ML workload, especially when it comes to training. AI ML workloads are very complex and mixed. They can be large block, and bursts of large block. So what we did some testing in our labs, on AI ML workloads running on Fibre Channel. Like I said, you could use different types of architectures. But shared storage is really important in terms of scalability. But when it comes to training, we believe on-prem infrastructure is best suited just due to the reliability, availability, and the performance requirements. And of course, costs. If you run this on a cloud, the cost can become really exorbitant. And then again, disaggregated storage solutions really solve the scalability and the cost requirements for AI/ML data sets. And then, training and speed and accuracy is highly dependent on the fabric. We ran some tests and we found containers running on NVMe or FC compared to, running standard FCP or running VMs over FCP, you get you really, really nice performance boosts when it comes to training data sets. And if you want more information on actual numbers, there's a recorded session on the Bright Talk we did about, I would say 6 months ago, which is recorded. So, again, just to summarize on AI ML, we have a lot of customers running AI ML workloads on Fibre Channel, especially FCME, running FCME on containers. This is something you may or may not be aware of, but keep in mind that, this is something that a lot of customers are, deploying, for a very contemporary workload, an old protocol like Fibre Channel. With that, I will hand it over to Craig to go into the deep dive into the protocol.
Okay, so the deep dive is into our newest speed, 128 GFC. Every single generation, I remember way back when we were doing 4 gig, the physical layer guys were saying, it's impossible. There's no way we can do 4 gig, and we just completed 128. And being a network, it's all about the cabling, and so the Fibre Channel has a number of different variants. We have the single mode variants, which are the very long distance, 2 kilometers or 10 kilometers, and then the multi-mode variants, which will go 60 meters over OM3 cabling and 100 meters over OM4, OM5. And of course, you have backplane for your enclosure type of applications. Signaling rate abbreviations, going all the way back to 1 gig. 20-something years ago, Rupin says it was like yesterday. I don't think so. That seems like a long time ago to me. But all the way up to now, we're just starting defining 256 GFC. And of course, the guys are saying again, it's impossible. There's no way we can do it. But they'll figure it out. The interesting thing on the number of lanes is the encoding. So in order to get these higher speeds, and I'll go into this some more, we have changed from NRZ encoding, which is a single bit per time clock, to PAM4, which is 2 bits per time clock, which basically gives you double the bang for your buck. So each time clock, you have 2 bits being transmitted. So that's what this is, modulation, which is the encoding. So 128 GFC uses PAM4, and so basically what you have is you have the bit rate or the clock running at 56.1, but your bit rate is 112. And that's what you get with the PAM4. Now, of course, the drawback of that is it does add some additional latency because you have a bit more processing taking place. It's in order to keep on using the OM4 and OM5 cables, you need to do something like this. Otherwise, you're going to much more expensive cables, possibly active cables that have chips in the ends or higher grade optics. And it's a good trade, we figured it's a good trade-off to use a little bit more latency so we can keep the same cabling plans. 64 GFC is the first speed where we started using PAM4, and if you look at the speed between 64 GFC, the base speed was 28.9, and the base speed of 32, which was NRZ or PAM2, was 28. So you can see that the clock didn't change that much. It was the encoding that gave you the bump. Now, of course, there's a little bit of an increase in the clock rate, and that gives you the extra parity bits you need for the error correction. This is demonstrated in pictures. If you look at the figures over on the right, you see the PAM2I, which is 1 bit, and which has one I, and this one on the bottom has basically 2 I's on the top and the bottom, which is basically 2 bits being represented on the signal trace. And another thing that we always maintain going backwards is we've been using the same transceiver modules almost back to 1 gig. Basically the SFP module, and so the modules are and do the optical and electrical encoding, and they do the clocking. And so also in the higher speeds, the clocking gets more difficult. We used to have analog clocks, and now we're going to digital clocks, just to handle the increased speed. But of course, clocking is very important because you need to make sure you match up the bit streams and you know when the ends and beginnings of blocks are. So the form factor for 128 GFC, it's the SFP 112. This is the SFP modules are defined by, which is what is now a SNIA group, the SFF. And so all the different variants, 100 meter, 2 kilometers, and the multi-modes all fit into this form factor. So if you look at a fiber channel link, starting out over at A, so what we do today, so you first go into a FEC encoder, which is your error correction mechanism, and then you go into your reclocker, which is your CDR, that go across the wire, you do another clocker, so the clocks always sync up, and then you go into a FEC decoder. And having those FECs obviously is an extra step. It adds a little bit of latency. And if you look at what happened, what the error correction does for you, if you did not have, at the, excuse me, at the speed we're going now, if you did not have an error correction mechanism in there, we would be at 1.31 to the 10 to the minus 4th bit error rate, but the FEC gets us up to 10 to the minus 15th. So, obviously, for 120 GFC, FEC is mandatory for all link types. If you didn't have FEC, you would start seeing potentially a lot of bit errors. Basically, FEC just works. It's a parity bit on steroids. There's multiple parity bits. The data is encoded in blocks which have enough redundant data so that there are multiple error bits or bit errors in that block. You can recover them. And so for 128 GFC, you can have 15 errors in one 5K block. And it can recover those. And as I mentioned, if we didn't have that, our error rate would be orders of magnitude smaller than it is. Well, however you want. I'm sorry, worse.
So then, I think this is where I can ask my question then. So it's 1 times 10 to the negative 15th is the target error rate.
That's right.
So we're doing 128 gigabits per second.
Mm-hmm.
So that's about, what is that, 10 errors in a minute?
Oh, it probably more, it's per second. Because if you're talking about 15 possible errors per 5K block.
I'm talking about 10 uncorrected errors.
Oh, effectively, we never see any uncorrected errors. because the cables are much better typically than 10 to the minus 15th. That's
So
just
if
that.
someone does do the base spec, that's about 10 errors a second, or 10 errors a
Repeat the
minute.
question.
So the question is, if given the math, is it 10 uncorrected errors per minute, is what you're saying? And the answer is that the actual cables that are built in components have a much better error rate than what is specified by the standard. So I wouldn't expect you to actually see any uncorrected errors in a normal running system.
But if they did,
It is within spec, yes.
and it's about 10 per minute.
I haven't done the math like that, so I don't, off the top of my head. So FEC has been around for a while. It started out in 16 GFC, where it was optional for optical links and mandatory for copper links. And then in 32 GFC had mandatory FEC as well as 64. And the FECs for 32 and 64 are very similar. 16 is the FECs for 64 and 120 are very similar. The FECs for the other speeds are different. And as I mentioned, the small baud rate increase from 64 to 32 is due to the additional parity bits. And the so if you look at some of the math here, the 32 added 140 parity bits, the 64 added 160, and 120 also 160. So the next big feature about Fibre Channel is the speed negotiation. How about being able to negotiate back to the last two previous speeds? In the old days, before 32 gig and below, Fibre Channel had a speed negotiation scheme which was kind of like, you would try matching your clocks. Did that work? Nope. Let's do this. Nope. Nope. And it worked. It was time consuming. And occasionally, it could be error prone. You could have bit aliasing, and you could have mismatched speeds locking. And then, of course, the link didn't work. And so you're in the data center unplugging and trying to figure out why. At 32 GFC, we fixed that issue we negotiate always to 32 gig, and then we in the training field, we say what speed we actually want to run at. And so the link then runs at the highest common speed from both sides. And so the training field also exchanges any information needed for the FEC type, the FEC information, as well as the transmission mode for FEC. And if anybody has more questions about that, I'm not going to go into more of those details. You can ask me offline. Transmitter training is a very important aspect at the speeds that we're running these days. Basically what it does is it takes stock of the cable and sets the coefficients for the receivers and transmitters so that they can run on the cable that they're connected by. And cables can vary for a lot of different reasons. You can have simply the length, you can have the quality of the connectors, you can have how good the connections are made in the SFP modules, whether there's dirt in there, so on and so forth. And so the training step, 420 GFC, is very important. When it was back in 16, it was an optional step. These days, it's a mandatory step. And of course, now on to our next big thing, which is FCPI 9. FCPI 9 is the next speed, which is 256 GFC single lane. It's being developed between the IEEE 802.3 group and the Fibre Channel T11.2 group right now. And as always, as I mentioned before, people are saying, oh, it's impossible. There's no way we can go this fast. We have the same goals as we have the other speeds. We want an OM4, OM5 reach of 100 meters, a single mode reach of 10 kilometers. We want to have the 256 gig links be a double of the speed of the 128, and we want to have the same bit error rate target. And every single time these requirements have been thrown out through all the speeds, they've always been able to meet them, even though we've always had discussions like, well, we're going to have to change the cabling, we're going to have to do this and that. But the guys who do the really low-level stuff always figure out how to make this stuff work. And so I'm going to end with the Fibre Channel roadmap here. This roadmap goes back to 8 gig, and 8 gig was available in 2008. And we go all the way up to the current speed, which is 128. The standard completed in 2022, and products will probably be available next year. Right now, we just started working this spring on the 256 gig GFC, and we expect that standard to be complete in 2025, and the products will be able when the market wants them. Typically, it's 2 or 3 years after the standard is completed. And so with that, I'll see if there are any additional questions. Yes?
Do you anticipate any link bring-up timing changes between 64 and
Well, yeah, and that was something that,
Repeat the question, please.
I'm sorry.
No worries.
Were there any the question was, are there any link bring-up timing differences between the different speeds? And that's where I alluded, I didn't go into it, but because of the digital CDRs, the link bring-up time has increased for those CDRs to lock. They have been doing some things to try to bring that down, but it's gone from 1 or 2 seconds to maybe 5 seconds, just because, or more, depending on the quality of the link. And they are doing a lot of work, because this is not a problem unique to Fibre Channel. It's also an issue with Ethernet, because Ethernet uses the same low-level encoding. Any other questions?
On the last chart, you were showing the generation time, looks like it's going to increase from like 2 years to 4 years.
They were 3 to 4 years.
Well, I mean, 2025, 2029, 2030, 2033.
Yeah, that's in the future.
I mean, when you're doubling the speeds at these high speeds, it's going to take more customers more time to saturate these higher speeds. So henceforth, the need to delay. Also, it's getting more and more expensive too.
And Rupin and I will probably be retired by the lowest one, so.
One more generation, and we're done.
So the goal is just to get generation past your retirement.
That's right, yeah.
It's being recorded, Craig.
In your crystal ball, you have an attach rate for 64 now?
See, I'm on the engineering side. I don't look at numbers. So I do know that so the question is there an attach rate? You mean a sales, how much people are picking up on 64? It always starts out very slow, and 64 start a little bit slower because initially there weren't as many components available. I do know that they're starting to ship now, but I don't know what the numbers are.
Yeah, I can comment on that a little bit. Like Craig mentioned, Fibre Channel is driven by the targets, right? So when more storage supports 64 gig is when customers will start thinking about upgrading the servers and the switching infrastructure, right? I think next year will be the transition point for 64 gig, where majority of the sales will be, next year will be 64 gig. Yeah. Any more questions? No, thank you.